Hello again. This is the second video for partition matrices. We're going to look at some practice problems. This is practice problem number 2 in the book. And what does the transpose mean of this partition matrix? Well, you do have to be careful with transposes as well. Yes, the rows become the columns and the columns become the rows, but each one of these is also have to be transposed. So not only do you have to transpose the partition, but you got to transpose each one. We don't know what those are, so we're just going to leave it like that. So what they would like us to do, so therefore, if I have times x, that's going to be what? This is a 2 by 1. This is a 1 by 2, so don't get that confused and make it a 1 by 1. This is actually a 2 by 2. And what is it going to be? What, 2 by 2? Well, we're going to do the first row. This one's the first row, first column. First row, first column. So it's going to be x1 transpose times x. 1. This is the first row, second column. So x1 transpose times x2. And then finally, the second row is going to be second row, first column, x2 transpose x1, and finally x2 transpose x2 should be the answer. Let's look at the solution in the book. You can see they got the same answer. And I just wanted to add what they had here. The partitions of x transpose nx are automatically conformable to block matrices, because you should worry that, well, what if we can not multiply those? But because the columns of the transpose are the rows of x, so you can easily take and multiply these. So if x is a m by n, x transpose is a n by m, and if you're going to multiply those together, so x transpose x would be actually n by n, because I do this one first. That would be a n by m times an m by n, and the result is an n by n. So you can see that it's automatically going to work. This partition of x transpose x is used in several computer algorithms for matrix computations, which is an application of a transpose of a matrix. Someone asked that in class the other day. Okay, let's look at number 21. Number 21 is an example of powers. So let's just do part A first before we get into the partitions. They just want to verify that a squared is indeed I. So what am I going to do? I'm going to just write down a squared twice. Write down a twice. A multiplied by a is what a squared is. And hopefully we get the identity. So let's see, we get the first row, first column, that would be this and this, so that would be 1 plus 0 is 1. This would be the first row, second column. First row, second column, you would get 0 with a 0. The second row, first column, would be a 3 with a negative 3, so that's also 0. And finally, last row with the last column is 0 with a 1. It does work. So we did verify that I squared is negative 1. Let's do part B over here. I like part B because it shows an example when you have a large matrix with a block of zeros. Partitioning them would be useful. And I'm just going to partition this way. It takes advantage of the block of zeros, and also takes advantage that I know A there. And I'm going to label this. Actually, let's put the B up here. I'm going to label this as A11 A12, A21, A22. Then I notice that this is just A. So A11 we know is just A. So I'm just going to write an A here. And A12 we know is just 0. So I'm going to make that 0. This right here is the identity. A21 is I. And then finally, A22, what is that? That looks like it's a negative A, doesn't it? So that's what I'm going to look at. So now if I take m squared, let's see if we do indeed get I. So let's do it the same way as we did part A. So we have a 2 by 2 with another 2 by 2. So we'll definitely end up with a 2 by 2. And what will we end up with? Well, I better make sure I have enough room there. We're going to have a squared. First row, first column, that's a 0. We're going to have here a 0 with a 0, so that's just a 0. Here we're going to have an A, IA with a negative AI. Both of them are A with a negative A. And then finally, we're going to have a 0 with an A squared. But we just showed that A squared was the identity. So that's like an I2, isn't it? Which is an identity matrix with partitions. So identity matrix, again, we've talked about that. I don't know what the size is. Actually, I do. It's because we know what this is. It's going to end up being I4. Makes sense, this 2 here. This is, right? What does this mean? I2, 0, 0 is actually 1s. And then this is 1s. Zeros are just the size they need to be, so they have to be 2 by 2. And you can see here where you do indeed get I4. We'll just make this a sense. So it works. There's the solution. So that concludes section 2.4, partitioned matrices.